class. I'm Spashni Muthalia. Let's study about the alcohol, phenol and ether. In the previous lecture, we have studied about the primary, secondary and the tertiary alcohols. So now we are going to study about the electronic structure of the alcohols. So let's continue with the terms. So electronic structure of alcohol. So see the structure over here. This is the carbon attached with the hydrogen, and hydrogen. So, and this attached with the oxygen and oxygen attached with the hydrogen. So we are having we know the sigma bond and the pi bond. We have studied in the 11th standard. So the single bond is a sigma bond and the double bond is a pi bond. So here the bond between the carbon and the oxygen is, and oxygen and the hydrogen is sigma bond. So the carbon and the oxygen is having a which hybridization? It's a sp3 hybridization. This also we have studied in the 11th standard. Now the angle between the CO and H is a 108.5 degree. CO and H. This is what? 108.5 degree. Okay. So this angle, so you have to remember it. Fine. So this is the electronic structure of the alcohol. They are having a lone pair. Fine. So the physical properties of the alcohol is what? In alcohol compounds, the electronegativity of an oxygen atom of a hydroxyl group is higher than the electronegativity of a hydrogen atom. So due to this, it induces partial negative charge, that is a delta negative, and oxygen atom and the partial positive charge, that is a delta positive, on hydrogen atoms. So oxygen del minus and the hydrogen del plus bond becomes polar. So the negative and the positive attracts to form a polar bond. And in the liquid alcohol, the intermolecular hydrogen bond is formed. So as a result, intermolecular attraction increases over here. The energy, higher energy is required to break these attraction forces. So if these are the more attractive forces in the molecule of a liquid alcohol, then more thermal energy is required. Thermal energy means what? Heat energy is required to break and to convert into the gaseous form. So the value of the boiling point increases. Thus, this type of hydrogen bond is not formed in the alkene before the polar bond is absent in them. Therefore, the boiling point of an alcohol are higher than those of the alkene, having approximately equal molar mass. So, obviously, the object is in the liquid form. The boiling point will be the more comparing to the higher as compared to the other molar mass, right? For example, boiling point of our ethanol, that is molar mass is 46 gram per mole. So the boiling point is 351 Kelvin, which is higher than the propane, that is molar mass is 44 gram, and the boiling point is 231 Kelvin. So the propane and the alcohol. So alcohol is in the liquid form, propane is in the gaseous form, right? And the boiling point of a propanol is 317 Kelvin. The molar mass is 60 gram. Propanol. Okay. So it is higher than the butane, that is 58 gram molar mass, and the boiling point is 273. So here it shows the intermolecular hydrogen bond between the alcohol molecules. Okay. Now the acidity of alcohol. Aqueous solution of alcohol possesses slight acidic property due to the polar OH bond present in them. Alcohol have an acidic property similar to that of water. So most of the alcohol except methanol are less acidic than water. So alcohol are OH plus water, the reversible process. It gives alkoxide ion. In alcohol compounds, an electron releasing group, that is RCH3, C2H5, so increases the electron density of a hydroxide bond. What is the electron density? The weight of the electron which is present in the compound is electron density. So the result is decrease in the polarity of hydroxide bond. As a result, the acidic property decreases over here. So thus the order for the acidic strength of the alcohol compound is primary alcohol is the more acidic strength than the secondary one, and then the tertiary alcohol. So this one you have to remember. That is, primary alcohol is more acidic than the secondary, and then secondary alcohol is more acidic than the tertiary alcohol. Okay. Now the preparation of alcohol. So alcohol is prepared from the alkene compound first of all. So by the name, this is important. It's coming the exam. There is according to the Markov-Nichols rule. We have studied in the 11th standard also. According to the Markov-Nichols rule, what was that? The double bond breaks and it is free. So the water is attached with the one hydrogen and one OH over here. So it forms the alcohol. So see here, CH3, CH, OH, and then CH3. So if in unsymmetrical alkene is used as a starting material, then the addition reaction follows the Markov-Nichols rule and gives the alcohol over here. So propane reacts with the water, it gives propane to all. Yeah. So see the mechanism over here. So alkene molecule accept a proton from aqueous acid H3O plus and form carbocation. So this is the alkene group, this is the water. So the bond goes from over here to here. It attached, it's as a slow process is there. So the bond goes from here to here. So it gives a positive charge. So the water, the particles H3O plus is there now. So hydrogen is replaced over here and forms the pair, lone pair like this. So in the step 2, nucleophilic reagent, that is the water attacks on the carbocation and forms protonated alcohol. Now the water is attacking over to the carbocation group. This is the carbocation group. So it forms a protonated alcohol. So the O plus, it forms again O plus and then hydrogen and then OH. So it's a protonated alcohol. So finally what happened? The proton is removed and an alcohol is formed over here. So the bond is goes over here and it forms like this alcohol, and again the hydrogen bond comes over here in this format. So COH alcohol group is formed. Okay. The next one is what? By hydroboration oxidation. For the preparation of alcohol in the laboratory, the indirect addition of water in the alkene compound can be achieved in the presence of diboron. So what is diboron? That is BH3 twice, or we can say H6, B2H6. Okay, so diboron reacts with alkene to give trialkyl borane as addition product, which is called hydroboration reaction. So the trialkyl borane is oxidized to alcohol by hydrogen peroxide in presence of aqueous sodium hydroxide. So let's write the equation in this format. Propane on the hydroboration, that is B2H6, it gives tripropyl borane, that is CH3CH2. The double bond, it forms like this, that is CH2CH3 thrice, and then B is over here. Okay. So again on the oxidation, it forms CH3CH2CH2OH 3 times propanol. So basically what is that? The propene, when reacts with hydroboration under process of hydroboration, it forms like this, one hydrogen over here and then BH2 over here. Again with the propane, it forms like this only, one hydrogen over here and BH2 over here. So twice is given over here, and it again continues pair. Lastly, we are getting it propanol plus H3BO3, boric acid. It's studied in 11th standard, right? So from carbonyl compounds, how it is formed? By the reduction of aldehyde and the ketones. Aldehyde and the ketones are reduced to the corresponding alcohols by addition of hydrogen in presence of catalyst. The catalytic hydrogenation, the usual catalyst is a finely divided metal such as platinum. Now the palladium or the nickel also is used as a catalyst. So it is also prepared by treating aldehyde and ketone with sodium borohydride, that is NaBH4, or lithium aluminum hydride, that is LiArH4. aldehyde yield primary alcohol, whereas the ketone gives secondary alcohol. So basically over here, RCHO plus H2 gives RCH2OH. It is in the palladium form, in the presence of palladium. Once the ketone group is taken over here, NaBH, it forms a RCHOH and then R dash. Okay, so this is from the carbonyl compound. Next, by the reduction of a carboxylic acid. So by reduction of a carboxylic acid and the esters, carboxylic acid are reduced to primary alcohol. In an excellent yield, we are getting the in a good form of the output by the lithium aluminum hydride, that is LiAlH4. So it acts as a strong reducing agent. So RCOH, carboxylic acid, in presence of LiAlH4, it gives RCH2OH. So LiAlH4 is an expensive reagent and therefore used for the preparing for the special chemicals only. Commercially, acids are reduced to alcohol by converting them to the ester, that is followed by the reduction using the hydrogen in the presence of catalyst. RCOH with the ROH gives RCOR. In the presence of catalyst, hydrogen catalyst, it gives a alcohol, that is RCH2OH and ROH. So in this way, we are getting the getting the reduction of the carboxylic acid, and we are getting the ester as well as alcohol. So from the Grignard reagent, the Grignard reagent is a very, very important topic. So alcohols are produced by the reagent of the Grignard reagent. So the first step for the ketone group is what? RNGX. RNGX is a Grignard reagent. So when this R is having a del negative and magnesium is having a del positive. So the negative is attracted to the carbon and the magnesium is attached to the oxygen. So this is in the primary reaction. It comes like this. There is a C, this attached to the carbon, and Mg is attached to the oxygen. So it forms this way. So again, addition of the water, what we are getting, that Mg is substituted by the hydrogen. So we get Cr and then OH, and here we are getting MgOHX. So the water, hydrogen comes over here and OH comes over here. So MgOHX. Okay. So RMGX is a Grignard reagent. From that, it is helpful for the production of the alcohol. See here, basically, this is the aldehyde, formaldehyde. When reacts with the RMGX, it gives RCH2O MgX, and finally what we are getting RCH2OH and MgOHX. So always remember MgOHX is be separated over here. So this is the primary, secondary, and the tertiary alcohol. So you will notice that the reaction produces a primary alcohol with the methanol, secondary alcohol with other aldehyde, and the tertiary alcohol with the ketone. Now let's study about the phenol structure. So aromatic structure with the alcohol OH, phenol, the common name is phenol, then OH, CH3, so it's a 2-methyl phenol. So the name of the 2-methyl phenol, the common name is what? Orthocresol. O is not what? Ortho. So see here, basically what we'll write, this is a phenol structure, catechol, resorcinol, and the quinol. So this is a position, which position is the ortho, meta, and para. Ortho, this is the ortho position, meta position, and para position. This is catechol, resorcinol, and the quinol. So you see here, this is number 1. This is 2, 3, 4, 5, and 6. 2-methyl phenol. 2-methyl phenol. So this one is a 1. This wherever, because hydroxide is more reactive than the CH3. So wherever it will go, it comes number 1 only. 1, 2, 3. So 3-methyl phenol. And here 4-methyl phenol. Or you can say paracresol. Why paracresol is there? Because OH toluene is toluene what? Methyl group is there in the aromatic structure. So its name is cresol. Fine. So catechol, when 2 hydroxide group is there, so it's a catechol, resorcinol, and hydroquinol. Same benzene 1,2-diol, benzene 1,3-diol, benzene 1,4-diol. Okay. So the electronic structure for the phenol is somewhat like this. The carbon and the oxygen and the OH bond is having a sigma bond. So this carbon is having a sp2 hybridization, and the angle between the carbon, oxygen, hydrogen is 109. So the angle between the carbon, oxygen and the hydrogen is 109 degree with the two dipole moment. So the preparation of the phenol is what? Phenol are known as a carboxylic acid, was first isolated in the early 19th century from a coal tar. So nowadays phenol is commercially produced synthetically in the laboratory. So phenols are prepared from the benzene derivatives by some methods. So there is from haloarenes. Chlorobenzene is fused with the sodium hydroxide at a present of 623 Kelvin and 320 atmosphere pressure. Phenol is obtained by the acidification of a sodium phenoxide. So, just see here, we have studied this in chapter number 10. If you remember it, chlorobenzene reacts with NaOH, gives ONA. With the HCl, it forms OH form. That is, from chlorobenzene to the phenol group, it forms like this. The second step is what? From benzene sulfonic acid. So from benzene sulfonic acid, how it forms? So benzene is again sulfonated with the oleum. Oleum is what? H2O7. So oleum, it gives SO3H. So in the presence of NaOH and hydrogen, it forms phenol. So benzene is sulfonated with the oleum and benzene sulfonic acid. So form is converted to sodium phenoxide on heating with a molten sodium hydroxide. Acidification of the sodium salt gives phenol. From diazonium salts, let's study what is a diazonium salt. So N2Cl is a diazonium salt. It is formed by treating an aromatic primary amine with a nitrous acid. There is NaNO2 with HCl. What is nitrous acid? NaNO2 with HCl is nitrous acid. Diazonium salt are hydroxides hydrolyzed to phenol by forming with a water or by treating with a diode acid. So aniline, NH2 with a benzene, NaNO2 with benzene diazonium. So how it forms? N over here, N2, right? HCl is there added over here, the chlorine comes over here, right? So water is there and then hydroxide forms. So what is taken out? N2 is taken and HCl is taken. So in that place, the hydroxide group is added over here. Now the fourth term is from cumene. Cumene is what? That one carbon is attached with the benzene ring and CH is attached to it. This is isopropyl benzene. So phenol is manufactured from the hydrocarbon cumene. Cumene is what? Isopropyl enzyme, which is oxidized in the presence of air to cumene hydroperoxide. It is converted to the phenol and acetone by treating with the acid. So when on oxidation of the cumene, we get cumene hydroperoxide. So with the hydrogen, we are hydroxide ion, we are getting phenol. And what is remaining? CaCO, that is the acetophenol. Acetone. So acetone is a byproduct of this reaction, is obtained in the large quantity by this method. There is a cumene method. Physical properties of the phenol is what? The phenol contains hydroxyl group. Therefore, in liquid state, it forms intermolecular hydrogen bond with one other molecule of a phenol with other molecule, water molecules, just like a alcohol. Hence, intermolecular attraction is increased over here. So due to this, phenol has a higher boiling point and more solubility is water than toluene, that's the arene compound, and fluorobenzene, haloarene compounds having approximately the same molecular mass. There is a molar mass. Phenol is a 94. See here, the molar mass of the phenol is 94, toluene is 92, and fluorobenzene is 96. What was the boiling point? It is decreasing. As increasing the molar mass, the boiling point is decreasing, and the solubility of water is this one. Okay. See here, intermolecular hydrogen bond among the phenol molecules, how OH is attached with the another phenol, and another phenol. So the intermolecular hydrogen bond between the phenol and the water molecules is in this way. Okay. So now physical properties of the isomer of a nitrophenol is what? So orthonitrophenol, metanitrophenol, and the paranitrophenol. The melting point is increasing according to the ortho, meta, and the para position. The solubility of water is also increasing over here in this format 0.2, 0.2, and 1.7. Okay. See here the intermolecular hydrogen bond among the paranitrophenol molecules. This is the N plus OH minus, and here it is interrelated over here. Now the intermolecular hydrogen bond between the paranitrophenol and the water molecule is somewhat like this. So how the bond, the ions, this is the positive and negative ion, positive and negative, how it is attracted over here. Now here is the intermolecular hydrogen bond that is in the orthonitrophenol. So the benzene ring and the NO group, NO2, and the water H2O group, NO and the H2O group, how it is attached over here. Thank you. Hope you understood the topic very well. Need to revise the chapter by reading and writing practice.